Welcome to the Software Engineering Music Deep Dive into Python. Whether you're new to the world of Python or a seasoned developer looking for a comprehensive refresher on how Python's object model really works, you'll find something valuable here. Today we're diving deep into one of Python's most sophisticated and elegant systems: classes, inheritance, and the method resolution order. This isn't your typical tutorial where we just show you the syntax. We're exploring the fundamental design philosophy behind Python's object-oriented programming capabilities and the thoughtful implementation details that make it all work seamlessly. Feel free to listen and absorb at your own pace. This is dense material that's worth revisiting. If you want to dive deeper into any of the concepts we discussed today, you'll find a comprehensive list of sources and additional reading materials in the description below. This is just one episode in our Software Engineering Music Deep Dive series, where we explore the fundamental concepts that make programming languages tick. If you'd like more content like this, where we go beyond surface-level tutorials and really understand the engineering decisions behind the tools we use every day, please hit that like button and subscribe. All right, ready to unlock the secrets of Python's object model? Let's dive in. Our journey into Python's object-oriented world begins with the fundamental concepts of a class and an object. What appears to be a single atomic action, creating an instance of a class, is in fact a carefully orchestrated two-phase process. Unpacking this sequence reveals a core design principle of Python: the separation of concerns, which provides powerful hooks for advanced customization and control. At its heart, a Python class is a blueprint or a template. Much like an architect's blueprint for a house, a class defines the structure, characteristics, attributes, and potential behaviors, methods, of something, but it's not the thing itself. When we define a class using the class keyword, we are not creating a tangible entity that holds data. We are creating a new custom type that Python can understand and work with. An object, in contrast, is the physical house built from that blueprint. It is a concrete instance of a class. While many houses can be built from the same blueprint, each house is a distinct entity with its own specific state. For example, one house might be painted blue and have 3 occupants, while another built from the identical blueprint might be painted green with 4 occupants. Similarly, multiple objects can be created from a single class, but each object holds its own independent set of data in its instance attributes. This fundamental concept of bundling data, attributes, and the functions that operate on that data, methods, into a single unit is known as encapsulation, a cornerstone of object-oriented programming. The two-phase creation, Dunder new and Dunder init. A critical piece of Python is the process of object instantiation. The expression "my class" looks like a single function call, but Python internally executes a two-stage protocol involving 2 distinct Dunder __ methods: Dunder new and Dunder init. The first method called is Dunder new. It is a static method, meaning it is bound to the class itself, not to any specific instance. Its first argument, by convention, is CLS, which is a reference to the class that is being instantiated, e.g., my class. The primary responsibility of Dunder new is to create and return a new, empty instance of the class. It is the method that actually allocates memory for the new object. Dunder init, the initializer, After Dunder new successfully creates and returns an instance, and only if it returns an instance of the correct class, Python then calls the Dunder init method. Unlike Dunder new, Dunder init is an instance method. Its first argument is self, which is a reference to the newly created instance that Dunder new just returned. The role of Dunder init is not to create the object, but to initialize it, to set its initial state by assigning values to its attributes. The Dunder init method should not return any value. Its purpose is to modify the instance in place. This separation of creation and initialization is not merely a procedural detail. It represents a fundamental shift in context from the class level to the instance level. When Dunder new is executing, it is operating on behalf of the class, CLS, before a specific instance has been fully formed. Its purpose is to construct the very object that will later be passed to Dunder init as self. Consequently, Dunder init's role is confined to configuring an object that already exists. This design is the enabling mechanism for several advanced Python patterns. For instance, while Dunder init is used in the vast majority of cases, overriding Dunder new becomes necessary for specialized tasks. Immutable types like strings, numbers, or tuples cannot have their values changed after creation. Therefore, one cannot modify them in Dunder init. To create a custom subclass of an immutable type, e.g., a tuple that has some extra methods, the customization must happen during the creation phase itself, which is controlled by Dunder new. The singleton pattern ensures that only one instance of a class ever exists. To achieve this, we must intercept the creation process. If the logic were in Dunder init, it would be too late, as a new object would have already been allocated by the default Dunder new method. By overriding Dunder new, we can check if an instance already exists in a cache. If it does, Dunder new can return the existing instance instead of creating a new one, completely bypassing the subsequent call to Dunder init for a new object. This two-phase protocol reveals a core Python philosophy, providing low-level, powerful hooks for developers who need to customize the fundamental behavior of the language. Anatomy of a class, state, and behavior. Once a class is defined, it serves as a container for two primary components: attributes, which represent its state, and methods, which define its behavior. The distinctions within these components, between shared and private state, and between different roles a method can play, are crucial for designing clean, maintainable, and efficient object-oriented systems. Within a class, attributes can exist in two different scopes, a distinction that has significant implications for memory usage and state management. The difference can be understood using the analogy of a residential apartment building. A class attribute is like the building's shared gym or rooftop terrace. It belongs to the building, the class, as a whole. And every resident, every instance, has access to the same one. Class attributes are defined directly within the class body, outside of any methods. They are stored in the class's special DunderDict attribute, which is a dictionary that serves as the class's namespace. Because they are shared, if the class attribute is changed at the class level, e.g., building.gym hours equals 24/7, that change is immediately reflected for all instances. An instance attribute is like the furniture inside a specific apartment. It belongs exclusively to that one resident, the instance, and is not shared with others. Instance attributes are typically created within the Dunder init method by assigning to self, e.g., self.sofa color equals blue. Each object maintains its own copy of instance variables stored in its own Dunder dict namespace. The attribute lookup chain. The way Python resolves attribute access is fundamental to understanding the interplay between these two attribute types. When a program requests myObject.x, Python follows a strict order of precedence. It first checks the instance's own namespace, myObject.dunderDict. If x is found there, its value is returned. If x is not found on the instance, Python then searches the namespace of the instance's class. Type myObject.dunderDict. If it's still not found, Python continues searching up the inheritance hierarchy according to the MRO, which we will discuss later. If the attribute is not found anywhere in this chain, an attribute error is raised. This lookup mechanism directly explains a common point of confusion: the behavior of modifying a class attribute through an instance. Python's rules for assignment and lookup are simple and universal. The rule for assignment is that instance.x equals value always creates or modifies the attribute in the instance's namespace, DunderDict. It never writes to the class's namespace. Consider a class car with a class attribute color equals red. If we create an instance myCar equals car, and then execute myCar.color equals blue, this assignment does not change car.color. Instead, it creates a new instance attribute called color on myCar with the value blue. This new instance attribute now shadows the class attribute. When myCar.color is accessed again, the lookup rule finds color on the instance first and returns blue. Other instances of car will still see the class attribute's value red. This behavior contrasts sharply with the modification of mutable class attributes. If car has a class attribute features equals, and a program executes myCar.features.append GPS, this is not an assignment. It is a two-step process. First, a lookup of myCar.features, which finds the shared list object on the car class. Second, an in-place mutation of that shared list by calling the append method. Because the list object itself was modified, this change is visible to all other instances of the car class. This distinction between direct assignment, which creates a shadowing attribute, and in-place mutation, which modifies the shared object, is a critical nuance derived directly from Python's fundamental rules of lookup and assignment. Just as attributes have different scopes, methods can have different roles depending on what context they are designed to operate on. Python formalizes these roles into three distinct method types. Instance methods. These are the most common type of method. Their first parameter is, by convention, self, which receives a reference to the specific instance on which the method was called. Instance methods are designed to operate on the state of an individual object, accessing and modifying its instance attributes. For example, a bank account object might have an instance method deposit amount, which modifies that specific account's balance attribute. Class methods. A class method is marked with the @class method decorator. Its first parameter is, by convention, CLS, which receives a reference to the class itself, not an instance. Class methods are used for operations that relate to the class as a whole, rather than a particular instance. They can access and modify class attributes, but not instance attributes, as they don't have a self. A primary use case for class methods is to define alternative constructors. A class can only have one Dunder init method, but it can have many class methods that act as factories, creating instances in different ways. For example, a date class could have a class method date.fromISO string 2025 July 19th that parses a string and returns a properly configured date instance. Static methods. A static method is marked with the @static method decorator. It does not receive any special first argument, neither self nor CLS. It is essentially a regular function that is namespaced within the class, primarily for organizational purposes. Static methods cannot access or modify either class or instance state. They are self-contained utilities that have a logical connection to the class, but are independent of its state. For example, a temperature converter class might have a static method, isValidTemperatureValue, that simply checks if a given number is within a plausible range. A task that requires no knowledge of any specific temperature conversion instance or the class itself. Choosing the correct method type clearly communicates our intent and helps enforce proper boundaries in class design. Inheritance is a mechanism that allows classes to be organized into hierarchies, enabling a new class to inherit the attributes and methods of an existing class. This promotes code reuse and creates logical is-AA relationships. Python supports both simple single inheritance and complex multiple inheritance, and its modern implementation, particularly the super function, is designed to handle these hierarchies in a robust and cooperative manner. In its simplest form, single inheritance involves a child class, or subclass, deriving from a single parent class, or superclass. The child class automatically gains all the attributes and methods of its parent and can use them as its own. It can also add new attributes and methods or, crucially, provide its own specialized implementation of a parent's method, a concept known as method overriding. When a method is called on an object of a child class, Python first looks for that method in the child class. If it's found, that version is executed. If not, Python looks to the parent class, and so on, up the hierarchy. This allows a child class to customize or completely replace the behavior inherited from its parent. A common requirement is for an overridden method in a child class to extend, rather than completely replace, the parent's method. To do this, the child needs a way to call the parent's implementation. This is where the super function becomes essential. While one could call the parent method directly using the parent's class name, e.g., parent.methodSelf, this approach is brittle and breaks down in more complex inheritance scenarios. The super function provides a more flexible and maintainable way to access inherited methods. A call like super.dunder init within a child's constructor ensures that the parent's initialization logic is executed, which is crucial for setting up any state defined in the parent class. The design of super is often misunderstood. It does not simply mean call my parent. More precisely, it means call the next method in the object's method resolution order. In single inheritance, the next in the MRO is indeed the parent class. But this subtle distinction is what makes super so powerful in the context of multiple inheritance. This design choice deliberately decouples the super call from a hard-coded reference to a parent. Instead, it is tightly coupled to the MRO, a dynamic sequence determined by the final object's complete inheritance graph. This means the behavior of super depends on the MRO of the instance, self, not just the class in which the super call is written. This is the key to enabling cooperative multiple inheritance, where each class, in a complex hierarchy, can perform its part of a task and then cleanly pass control to the next class in the chain, as defined by the MRO. Python's support for multiple inheritance allows a class to inherit from several parent classes simultaneously, combining their functionalities. While powerful, this capability introduces potential ambiguities that must be resolved systematically. The classic illustration of this challenge is the diamond problem. The scenario is as follows. There is a base class, let's call it A. Two separate classes, B and C, both inherit directly from A. A final class, D, inherits from both B and C. This creates a diamond-shaped inheritance graph, D at the bottom, B and C in the middle, and A at the top. The ambiguity arises if class A has a method, say M, and both B and C override this method with their own implementations. If an object of class D calls M, and D does not have its own override, which version should it inherit? The one from B or the one from C? Without a clear, deterministic and predictable rule, the program's behavior would be ambiguous. The order of method resolution could depend on subtle implementation details, leading to code that is difficult to reason about and maintain. This is the central problem that Python's method resolution order is designed to solve. The rules of succession. To make multiple inheritance a reliable and usable feature, rather than a source of chaos, Python employs a well-defined algorithm to determine the order in which to search the class hierarchy for a method. The MRO provides a single, unambiguous path for method lookup, elegantly solving the diamond problem and other potential conflicts. In any multiple inheritance system, the potential for name collisions is high. If a class inherits two methods with the same name from different parents, the language must have a consistent rule for deciding which one to use. An unpredictable or inconsistent MRO would make large object-oriented systems fragile. We could find that adding a new class to a hierarchy unexpectedly changes the behavior of existing code, a debugging nightmare. Python guarantees that for any class, there is a linear, predictable sequence of all its ancestor classes, starting from the class itself and ending with the base object class. This sequence is the MRO. A developer can inspect the MRO for any class by accessing its Dunder MRO attribute or by calling its .mro method. When a method is called, Python simply traverses this list from left to right using the first implementation it finds. Since Python 2.3, the MRO has been calculated using the C3 linearization algorithm. This algorithm was chosen because it has several desirable properties that ensure the resulting MRO is logical and stable. Rather than focusing on its complex mathematical formula, it is more useful to understand the principles that C3 is designed to uphold. The primary goal of C3 is to create a consistent MRO that respects two key rules: preservation of local precedence order. When a class is defined, the order of its base classes matters. If a class is defined as class D, subclass of B and C, the C3 algorithm guarantees that B and its ancestors will always be searched before C and its ancestors in the MRO of D. This honors the explicit ordering provided by us. Guarantee of monotonicity. This is a crucial stability property. It states that if class C1 precedes class C2 in the MRO of a class, then that relative order, C1 before C2, must be maintained in the MRO of any of its subclasses. This ensures that extending an inheritance hierarchy does not retroactively change the behavior of its parent classes. It makes the system predictable and robust against changes. Conceptually, the C3 algorithm constructs the MRO by performing a merge of the MROS of the parent classes. The process can be thought of as follows. Start with a list of the parent MROs. At each step, look at the first class, the head of each list. Select the first head that is good, meaning it does not appear anywhere in the rest, the tail of any of the other lists. This good class is added to the final MRO, removed from all the lists it appears in, and the process repeats. This rule ensures that a child class is always resolved before its parents, satisfying the inheritance hierarchy. A critical feature of this system is that failure is an option. If the C3 algorithm cannot find a consistent order that satisfies both local precedence and monotonicity, it fails. When this happens, Python raises a type error at the moment the class is defined, preventing the creation of an ambiguous class hierarchy. This behavior embodies a core tenet of the Zen of Python. In the face of ambiguity, refuse the temptation to guess. Python chooses to fail loudly and early at class creation time, rather than allowing for silent, unpredictable behavior at runtime. This choice for robustness and explicitness is a deliberate design decision that makes Python's multiple inheritance a powerful and safe tool for us. Python's class system does not exist in isolation. It is deeply integrated with the language's core syntax and built-in functions. This integration is achieved through a protocol of special methods whose names begin and end with double underscores, colloquially known as Dunder methods or magic methods. Understanding this protocol is key to creating custom objects that feel native to the language. Dunder methods are not truly magic. They are a well-defined and public protocol for operator overloading. They allow us to define how instances of our class should behave in response to common operations. When we write intuitive syntax, like A plus B or len C, the Python interpreter translates these operations into specific Dunder method calls, such as a .dunder add B or C.dunder len. By implementing these methods, a custom object can speak the native language of Python, allowing it to be used with familiar operators and functions in a way that is readable and Pythonic. A wide range of Dunder methods exists to customize nearly every aspect of an object's behavior. The following are among the most important for creating well-behaved custom objects. These two methods control how an object is converted to a string, but they serve different audiences. Dunder str defines the informal or user-friendly string representation of an object. It is called by the print function and the str type constructor. The goal is to produce an output that is readable to the end user. Dunder REPR defines the official or developer-focused string representation. It is called when an object is inspected in an interactive interpreter or by the repar function. The goal is to be unambiguous and ideally to return a string of valid Python code that could recreate the object. Object comparison, Dunder EQ, etc. By default, the equality operator equals checks for object identity. That is, whether two variables refer to the exact same object in memory. To define value-based equality, a class must implement comparison Dunder methods. Dunder EQ defines the behavior for the equality operator, equals. It should return true if the two objects are considered equal in value, and false otherwise. Other comparison methods include Dunder NE, not equal, Dunder LT, less than, Dunder GT, greater than, and so on. A powerful use of Dunder methods is to make a custom object behave like a built-in container, such as a list or dictionary. Dunder len, for length, allows the built-in len function to work on an instance of the class. It should return the number of items in the container as an integer. Dunder getItem enables subscription, allowing items to be accessed via square brackets, e.g., myObject, open bracket key, close bracket. This method is also what makes an object iterable. As for loops, we'll use it to access items by index until an index error is raised. Dunder setItem enables item assignment for mutable containers, e.g., myObject, open bracket key, close bracket equals value. Dunder delItem, for delete item, enables item deletion using the delete statement, e.g., delete myObject, open bracket key, close bracket. Dunder contains enables the use of the in and not in membership test operators, e.g., item in myObject. Context management, Dunder enter, Dunder exit. These two methods implement the context management protocol, which allows an object to be used with the with statement for safe and automatic resource management. Dunder enter self. This method is called at the beginning of the with block. Its job is to set up a resource, e.g., open a file, acquire a lock, and optionally return an object that can be used within the block. Dunder exit self exc underscore type, exc underscore value, exc underscore traceback. This method is called when the with block is exited, regardless of whether an exception occurred. Its primary job is to clean up the resource, e.g., close the file, release the lock, thus guaranteeing that resources are not leaked. The three arguments passed to it will contain exception information if an error occurred, allowing the context manager to optionally suppress the exception. In Python, many common operations on objects are actually just syntactic sugar for calls to special methods known as Dunder methods, those with double underscores before and after their names. Each operation we perform, whether it's creating, comparing, indexing, or printing objects, is powered under the hood by one or more of these Dunder methods. Let's walk through them one by one. When we create an object by calling a class like object equals myClass, open close parentheses, Python first uses the Dunder new method to allocate memory for the new object. Immediately after that, it invokes Dunder init to initialize the object's state. These two methods, Dunder new and Dunder init, form the core of object creation and initialization in Python. If we print the object using the print function, Python will call the Dunder str method to get a user-friendly string representation. This is what we typically see in logs or terminal output. But if we simply type the object into the interpreter without using the print function, Python instead calls the Dunder repr method. Dunder repr is expected to return a more precise, often code-like representation that's aimed at developers. Ideally, it should return a string that, if evaluated, would recreate the object. When comparing objects using obj, 1 equals obj2, Python relies on the Dunder eq method. This lets us define what equality means for our objects, whether we're comparing identity, value, structure, or some domain-specific logic. If we want to get the length of an object using the len function, Python will call Dunder len. By implementing this method, we can make our object behave like a sequence or collection, returning the appropriate count. For accessing elements using square brackets, like myObject, open bracket key, close bracket, Python uses the Dunder getItem method. This enables dictionary-style lookups, list-style indexing, and iteration over custom containers. If we want to assign a value to a key using myObject, open bracket key, close bracket equals value. Then Python uses Dunder set item. Similarly, if we delete an item using del myObject, open bracket key, close bracket, Dunder deletem is invoked. Membership testing, like item in myObject, calls Dunder contains. We can implement this to define what it means for something to be considered in our object. For example, we could check keys in a dictionary or elements in a custom collection. Finally, if we want to use our object in a with statement for context management, like opening a file or acquiring a lock, Python expects our object to implement both Dunder enter and Dunder exit. Dunder enter sets up the context, and Dunder exit handles any cleanup when the block exits, whether normally or due to an exception. To recap, here's the mapping. Object creation, Dunder new and Dunder init. Printing, Dunder street. Interactive display, Dunder REPR. Equality comparison, Dunder EQ. Length, Dunder len. Indexing, Dunder get item. Assignment, Dunder set item. Deletion, Dunder del item. Membership testing, Dunder contains. Context managers, Dunder enter and Dunder exit. By defining these Dunder methods in our class, we allow our objects to seamlessly integrate with Python's syntax, behaving like native types and enabling intuitive, readable code. That's it for today's video. If you found this content enjoyable, please remember to like and subscribe for more. Good night.